In this video, we will discuss finding the mean of a probability distribution. How do we compute the mean number of spots that show up on top when a die is rolled? We could try rolling the die 10 times, recording the number of spots and taking the mean, but the answer would only be an approximation. The more times we roll the die, the better the approximation, but to get the actual value of the mean, we must roll the die an infinite number of times. And that's impossible. A new method of computing the mean is necessary. Suppose two coins are tossed repeatedly and the number of heads is recorded. What will be the mean of the number of heads? The sample space is heads, 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 tails, tails, heads, tails, tails, and each outcome has a probability of 1/4. In the long run, we expect two heads to occur 1/4 of the time, one head half of the time, and no heads 1/4 of the time. On average, we expect the number of heads to be 1/4 times 2 plus 1/2 times 1 plus 1/4 times 0 equals 1. If we toss the coins many times, the average number of heads per flip will be 1. Here's the formula for the mean of a probability distribution. The mean of a probability distribution with a discrete probability distribution is mu equals x1 times the probability of x1 plus x2 times the probability of x2 plus a bunch of other stuff plus xn times the probability of xn. And that's all equal to the sum of x times the probability of x, where x1, x2, and so on are the outcomes, and p of x1, p of x2, and so on are the corresponding probabilities. Note, the sum of x times p of x means to take the sum of the products. The rounding rule for the mean, variance, and standard deviation for a probability distribution. The mean, variance, and standard deviation should be rounded to one more decimal place than the outcome x. When fractions are used, they should be reduced to lowest forms. For example, find the mean of the number of spots that appear when a die is rolled. We take mu equals 1 times 1/6 plus 2 times 1/6 plus 3 times 1/6 plus 4 times 1/6 plus 5 times 1/6 plus 6 times 1/6. That's 1/6 plus 2/6 plus 3/6 plus 4/6 plus 5/6 plus 6/6. And that's equal to 21/6, or 7/2, which reduces to 3.5, or 3.5. There is our mean, 3.5. Another example. In families with 4 children, find the mean number of children who will be girls. First, we find the sample space. And here we have 16 different options, from all boys to all girls. And I've listed the number of girls in each arrangement. There are 0 in all boys, 1 for BBBG, 1 for BBGB, and 2 for BBGG, and so on. And now we can make a probability distribution from the sample space. So here is the number of girls, and here's the probability. The probability of having 0 girls is 1 in 16. The probability of having 1 girl is 4 in 16, or 1/4. The probability of having 2 girls is 6 in 16, or 3/8. The probability of having 3 girls is 4 in 16, or 1/4. And the probability of having 4 girls is 1 in 16. We calculate the mean. The mean is 0 times 1/16 plus 1 times 1/4 plus 2 times 3/8 plus 3 times 1/4 plus 4 times 1/16. That's 0 plus 1/4 plus 6/8 plus 3/4 plus 4/16, which is 1/4 plus 3/4 plus 3/4 plus 1/4, which is 8/4, or 2 girls on average, which kind of makes sense. 50-50 chance of having a boy or a girl, approximately. And so if we're having 4 kids, we would expect about half of them to be boys and about half of them to be girls. Another example. If 3 coins are tossed, find the mean number of heads that occur. So first we find the sample space. There are 8 possible ways for 3 coins to be tossed. 1 is all heads, 1 is all tails, and then the others are distributed. 3 that have 2 heads and 3 that have 1 head. We construct our probability distribution. The number of heads is 0, 1, 2, or 3, and the corresponding probabilities is 1/8, 3/8, 3/8, 1/8. We calculate the mean. Mu equals 0 times 1/8 plus 1 times 3/8 plus 2 times 3/8 plus 3 times 1/8. And that's 0 plus 3/8 plus 6/8 plus 3/8, which is 12/8, or 3 halves. 1.5 heads per toss on average.